Okay, we're on the screen there. I want to kind of redeem myself a little bit. Well, there's no redemption. I was stupid. You should always, 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 even if you think you know a subject backwards and forwards, you should always before you show your ass in front of 190 students, which is basically what I did on two of those problems. You should go through the thing first and go, oh, okay, then reason through it so you can explain it. Now, the explanation I was given for why I chose a certain answer were all good, but I left some things that I didn't think through the problems correctly. All right, so I wanted to just kind of um, go through these things one more time because several of you missed, not that many, because I actually put in the grades for those who came. Not many missed, but enough. So let's just take a look at this thing. Going to knock me off here, and here we go. So let's go to the slideshow from the current slide. All right, now displacement, we're going straight from here to here, which depends on the location of A, depends on the location of B, the direction of A to B depends on that, and the shortest distance from A to B. All right. What it doesn't depend on is the distance traveled from A to B, because the distance traveled, that's the total distance. Okay. And that doesn't matter. So that does not depend on that. All right. Now here, is this the one where, okay, a displacement vector is from an object's final position towards its initial. No, it's the other way around. It's always directed along a tangent to the object's path. Okay, some of you wondered about the tangent to the object's path. I kind of showed you that. Basically, real quick, I want to go through that real fast. It's a little bit of a calculus lesson, but even if you haven't had calculus, I think you'll be okay with it. Just a second, I'm waiting for my ladybug to come on here. And so let's take a peek real quick. Come on, ladybug, fire up. I should have fired her up before man, it's taking a while. There we go. Now I think I have to do this again. Yeah, okay. Goodness gracious, I should have that set up. I've looked at some of my videos. I don't know how the hell y'all sit through some of these things. Anyway, so tangent to the curve, right? Isn't that what we were talking about? All right, now in calculus, when we're looking at that instantaneous, that delta x over delta t, which gives us our instantaneous velocity. Actually, in calculus, we write it as dx over dt because that means it's getting infinitesimally close. Well, what we're doing there, let's say you have the motion of something that looks like this, okay? And this is the time versus the distance graph, okay? The time versus the distance graph. So this is a good place to kind of do this. So look what's happening here. Look what's happening. I should have drawn my zero at a better spot. But anyway, from right here, it looks, see, we're taking off, we're leaving the house, and we're accelerating. And so if I take the derivative of the motion, there's a tangent line. There's a tangent line. Where there it looks like the tangent line is zero. So what does that mean? The tangent line is zero. If we're doing a change in x or a change in t graph, well, you remember your rise over run. This means I'm at zero. I'm not changing. Changing x or changing, I haven't changed. But that means I've stopped and I'm starting to come back the other way. And then I come back home to here, and then I keep going. And so these are tangent lines. These are tangent lines. And what they are is you take the derivative of the function. Oh man, I've lost some of you here. You take the derivative of the function at this point, and that tells you my instantaneous speed at that point. That's basic. That's the big idea of what's going on there. Okay. All right. So that's what that tangent line thing meant. Probably more explanation than you wanted or needed. Okay. All right, is this one in an area two planes are traveling due east. One plane has a larger acceleration than plane 2 has. Both accelerations are in the same direction. Which of the following statements is true concerning this situation? In the same time, plane 1 has a larger acceleration, so we knew that one was B. Okay, that was a common sense. Now, which of the following is defined as the distance traveled divided by the elapsed time for the travel? If you're looking at the total distance travel, you're looking at the average speed. Okay, total distance, where if you're looking at the displacement, you're looking at the average velocity. All right, now this is what I screwed up on. This is actually the instantaneous velocity, not the average, because it's traveling. It started from rest, so v naught is equal to 0, and then v final is the instantaneous velocity after an hour it's been running. It's 28 meters per second. So at that moment, at that precise moment, it's going 28 meters per second. So that would be the instantaneous velocity. I screwed that one up. Because at that exact moment, if we were doing the final velocity, and if we wanted to come up with the average acceleration, now it might have gotten up to 28 meters to, it went from 0, say, to 28 meters per second, say in 3 or 4 minutes instead of an entire hour. Then it's cruising along at 28 meters per second for a long time. So but the average acceleration, we don't know the instantaneous, but the average acceleration would be 28, would be this. So let's just see what it would look like. So on that slide, the average acceleration, which is mainly what we deal with, would be the 28 meters per second minus 0 over the 3,600 seconds. Notice, I get my meters per second squared here, and so that's a very small acceleration. But it probably, if we look at the velocity versus time graph of this thing, which is kind of like this one, it probably went like this. The velocity went very, very fast, and then it planed out like this, where the acceleration here is equal to 0, because the slope of the line is equal to 0. All right, this is dv dt is equal to the acceleration. So you're getting conceptual calculus here a little bit. But right here, say this happened within, 6 minutes, 360 seconds. It takes a while for 360 seconds. Right here, this time frame, this is from 0 to 360. 360 seconds. So in the first 6 minutes, it had this acceleration. And then you'd have the acceleration is equal to 28 meters per second between here and here, divided by let's say 7 minutes. Let's go 420, so it comes out even over 7 seconds, and you'd have an acceleration of 4 meters per second squared for those 7 minutes. Okay, and then your acceleration is equal to 0 here. So your acceleration here is the slope of the tangent line, which is equal to 4 meters per second squared. All right, so there's a lot going on in these things. Let's go on to the next. Let's do the last couple where I embarrassed myself. So here we go. Okay. Now, sports car starts from rest. After 10 seconds, the speed is 25. What is the magnitude of the car's acceleration? We knew that one. I just did that calculation. This is, which ones of the following situation is possible at a given time t? An object has an instantaneous velocity of 0 and an acceleration. If it stopped, that would be an instantaneous velocity of 0. That could mean it's turning back around or something. An object has of 0 and an acceleration with a magnitude greater. I wonder if that's possible. Oh wow, this is one of the, this is one we didn't do. Choices A, B, and C are possible situations. All of them. I was going to say all of them are possible. This is going at a nice constant speed right here. Nice constant speed. Instantaneous of 0 and an acceleration with a magnitude of, okay, it starts off as 0, but this would be if I drop something. For a split and instantaneous moment at 0 meters per second, but but the pull of gravity is 9.8 meters per second. No, here's where I dropped something. Here's where this is when we're turning back around. Okay. Or we're taking off. I'm at 0 meters per second, but boom, I get a thrust. All right, so all of those are possible. Where's the one I screwed up? Which of the following is not a vector quantity? Average speed. What are all these? Where's the one where I screwed up? Where the two planes or something? What happened to that one? Well, I wonder if I erased it. Huh. Okay. Anyway. All right. So there we kind of reviewed yesterday's quiz. Where's the one I screwed up? I don't know what happened to that slide. Oh, well. Life with Professor Riggs. There you go.